What we're going to do today is look at ASCE 7-10. This is the new version. You can see that by looking at the other versions of ASCE 7 that it's bigger. It's new. And this isn't really that new in a way. This has been out since April of this year, somewhere around there it's been out, but nobody's paid any real attention to it because it's not in the codes yet. And the building code, which is International Building Code, it refers to 05. The new version comes out 2012. And in 2012, it's going to refer to ASCE 7-10. And when do we expect that? It's probably going to be early in the year. In other words, maybe February or March, somewhere in there, we'll have the new code. This is 09. It'll be 2012 IBC. So we want to look at the new version and compare it to the 05. They look a lot alike, but it's billed as the most significant change to ASCE 7 since 1995. 1995 was the time that we switched to 3-second gust speeds instead of fastest mile wind speeds. So this is a significant change, but it's a significant change in a lot of areas besides wind. And as you're probably well familiar, the document carries a lot of information that is not wind resistance of roof. And the biggest expansion in 10 is really in the seismic area, earthquakes. And there's differences all through the book. It's reorganized, and it's considerably larger than the older version. This has got 600 pages compared to about 400. And it's not in the wind area for roofing. It's in a lot of different areas. Just before we get started on the differences, I'm going to recap real quickly wind design according to ASCE 705. And the basic equation for the wind uplift pressure, uplift, is going to be the velocity pressure times the exterior coefficient and the interior pressure coefficient together, and you'll end up with the uplift pressure. Most of the changes in 10, ASCE 7-10, occur in this area, which is velocity pressure. Now, velocity pressure is going to be looking at a constant times the exposure coefficient times the directional coefficient times the coefficient that adjusts for terrain. Unusual terrains like being on a cliff or an isolated hill, times an importance factor times velocity squared. And one of the important things in there to look at is velocity is squared. But once you end up with that, working that calculation, you will be calculating the pressure of the wind against an object at the height of the roof. And that can be expressed in Q sub H or Q sub Z. They're both the same as far as wind design is concerned. But what you're calculating is the velocity pressure against the building at the height of the roof. The next thing that you do is convert that velocity pressure into uplift pressure in 3 zones on the roof. The field of the roof has the lowest uplift pressure, and the perimeter second lowest, and the corners have the highest uplift pressure. And these numbers for GC sub P, this factor right here, is either going to be negative 1.0 or a negative 1.4, depending on how tall the building is. There's a break point at 60 feet. You know, buildings above 60 feet are going to be, in the field of the roof, is a negative 1.4, and you can see how that works. This doesn't really change in ASCE 7-10. That's going to be the same in that area. There will be some changes that just happen because of just small changes in the method of calculating. The third step in calculating pressure is to identify this product right here, which is the internal pressure coefficient. Internal pressure coefficient is a result of wind blowing against the building, leakage into the building that's greater than leakage out. So pressure builds up, it goes up through the deck and acts on the membrane and adds to the uplift created by the wind passing over the top and creating suction on the membrane. This is only going to be one of 3 values. If it's an open building, meaning there's no walls on the floor immediately below the roof, it's 0, so it doesn't really affect the value. But there has to be a definition of whether it's enclosed or it's partially enclosed. And partially enclosed is one where windows have been blown out in a storm, or there are large openings in a building, and that creates additional pressure on the inside, creating additional pressure, uplift pressure on that roof. So the definition of these two becomes important. That's a pretty big factor in the design of the uplift pressure on the roof system. So those are the 3 basic steps, regardless of whether you're in 05 or in 10, except a little difference in 05 as we'll go through. So what's new about ASCE 7-10? And in a word, it's the wind speed maps. Now, if you've opened that book, you'll kind of take a step back and say, those are considerably different wind pressures than I'm used to, or wind velocities. And the first thing I did after opening that book and looking at the maps is to say, wow, I wonder if they've changed the formula. So you look at the formula, and it hasn't changed that much. They've substituted 3 wind pressure maps for 1 map, and they've taken out the importance factor, but the numbers are going to be quite a bit higher. Now, as we go through this, you'll find that really gets canceled out in the end. So we have 3 different maps with different velocities instead of having an importance factor. So without an importance factor, we just choose the right map. It sounds pretty simple because most everything else is the same. This is the familiar ASCE 7-05 map, and that shows the wind velocities in the major part of the U.S., and then this is the hurricane-prone region where the hurricanes come in offshore. In the ASCE 7-10, we have the roof. This is the risk index. And we have a Category 1, a Category 2, and a Category 3 and 4 wrapped in this 3rd map. All of these maps have the same contour lines on them, but the wind velocities are higher on one than they are on the other. So we're going to end up with 3 different maps instead of 1 map, and we don't have an importance factor in the equation. And that's the main difference in that system. So look at the wind velocities and see how they compare. We have ASCE 705, where the main part of the U.S., now remember that the 3 states on the west coast are 85 miles an hour. The main part of the U.S. is 90 miles per hour wind. And then you end up with hurricane-prone regions running from 90, above 90 to 150. That's what we're used to in 05. In 10, importance factor 1, or in this case it's going to be risk category 1, using that map, the main part of the U.S. 105, Pacific coast is at 100, and then we end up with 105 to 170. Now that value can go up to 200 miles an hour in risk categories 3 and 4. So these are substantially higher winds in these cases. And the winds actually correlate with the recurrence interval. Now you're familiar with that in the ASCE 705. Category 2 is going to be our 50-year recurrency interval. That's 50-year recurrency interval will be on ASCE 705 map. But when we go to ASCE 710, even in risk category 1, we'll end up with a mean recurrence interval of 300 years. And you go into the standard building, which is not a high-risk building, and it's not a low-risk building. You're at 700 years, and in 3 and 4, 1,700 years. Dave?
Jerry, is it going to be the local code officials that determine which category they want to apply for the particular regions?
The question has to do with who determines what category you're going to be on, and that's a good question. We're going to spend quite a bit of time on that because the definition is not nearly as clearly defined in ASCE 10 as it was in 05. But you're going to have to make that decision probably with an owner. Why the higher wind speeds? This is probably one of the most important slides in this presentation, just to get your head around what is happening here. In ASCE 705, these were basic wind speed map, had a 50-year recurrency interval, and it was appropriate risk for components and cladding. These are things adhered to a structural element that is not going to fail. When these wind speeds were used for strength design, you'd have to go further than that at the end for the strength of the building and multiply it times 1.6. And most of us are not involved in strength design. So we've never seen this part of it. But we'll use the 50-year recurrency interval, and if you're designing the structure itself, you'll multiply it times 1.6. In the new version, we're using strength designed wind speeds. And these are used to calculate wind pressures on the main wind force resistance system. And the load factor is 1.0. Instead of having a load factor of 1.6, we have a load factor of 1.0. But in the components and cladding, the calculated wind pressure is multiplied by a load reduction factor of 0.6. And that's because we're using ultimate wind speeds for strength design, but we're using a lesser wind speed actually for components and cladding, and that adjustment at the end is going to be a 0.6 multiplier. Any questions about that side? This is found in Chapter 2. It's not really clearly stated. It's unfortunate that it's not as clear as it is, but for those who use ASCE 7 for whole building design, this is a lot more familiar to them, because you'd never build a building to a load factor where the structure would have a wind exceeding that once every 50 years. I mean, you're going to build that building so that it never blows down, period. And that's what they're used to doing, and multiplying the value with the old map by 1.6. So the change in equation is in the velocity pressure area. This is velocity pressure at height h, which is the height of the building. And you'll see that the same constant, same values. This is 05. And in the 10 version, the same equation, except you don't see the importance factor in it anymore. Two things have changed. The importance factor has been dropped, replaced by basic wind speeds, and the basic wind speeds have increased. So we've got higher wind speeds, but we no longer have that importance factor. The rest of the equation, the basic major equation, uplift pressure, velocity pressure, times the coefficient for internal pressure or external pressure and internal pressure, that remains exactly the same. But this is the part that has changed. And there's some subtleties that are also affecting these two as well. But we'll go through those and just see how they affect that area. You had asked the question about about who chooses the risk factor. Well, there are definitions. In 05, these are the major definitions for the three importance factors. It's occupancy category 1, buildings that represent low hazard to human life. That's going to remain the same. Category 2 says anything that's not 1 or 3 or 4 is in 2. It still is going to be there. But occupancy 3 and 4 were carefully defined. Now I'm going to go through those definitions, even though it's a little bit laborious, but go through the definitions to show how you would be told pretty much in 05 whether it's a category 3 or 4 or a category 2. So we have a lot of carefully defined building types that pose extra risk to people or contents of the building. In 07, we call 07-1